Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will continue talking about regularization for some time. We still have few techniques to cover, and then we will start a very important session about transformers, inshallah. Now we will talk about three different techniques: transfer learning, multitask learning, and self-supervised learning. All of them are nowadays very hot research areas. There's a lot of work on these techniques. Unfortunately, we don't have time to cover details. We will just introduce them, give quick definitions about the main ideas behind them. But actually, each one of these might be a course by itself. And there are actually some existing courses in the world about these topics. So mainly these topics or these techniques we use especially when we have very little training data. So we have a task we want to perform, and we have very little labeled data for that task. What we can do is different ways. The first one is called transfer learning. In transfer learning, we assume that we have another task that is related to the task that we are performing. And for that other task that we call secondary task, we have so much labeled data already. So for example, let's say that the primary task, the task that we are concerned with, is detecting the depth in an image. So for each pixel in an image, we want to know how far it is from the cameraman, which is the task here. And we assume here that we have very little labeled data for that task, but we have so much data for another task, which is the segmentation task. Segmentation task means that given an image, we want to classify each pixel to which object it belongs. So all pixels that belong to the same object will be the same, will have the same value or the same class. Type. Is the secondary task here really related to the primary task? Yes, if we have a model that understands how to segment objects, probably it will help doing the task of predicting the depth. For example, the pixels that are all belong to the same object might be very similar in depth than others. So what we do is that because we have so much labeled data for the secondary task, we build a model for the secondary task. And that model, of course, has an output layer for the segmentation task, right? After we build that model, for which we have lots of data, lots of labeled data, we use the same model, but we will continue the training on the primary task, for which we have very little labeled data. So we will get rid of the segmentation output layer, and we plug in another output layer for the depth task, or whatever the primary task is, and continue training the model. So this model here that is trained already for the secondary task will be used in training for the second task. Okay. طيب. What's the benefit that we did? Why don't we just train a model from scratch? Why do we need to train a model for a secondary task and then continue training for a primary task? Why don't we do it from scratch, from the beginning? We will know the parameters, we will know the depth of it, and then we can enhance. But we don't have labeled data for the depth for the first model. The first model is trained on the segmentation task. So this model is trained for the segmentation task. We will take it and continue training it, but for the depth task. They are related. So it should benefit from the knowledge that the model got from the first task. That's why it's called transfer learning. So it's like now we are transferring the knowledge from the task for which we have lots of data, lots of labeled data, to the task that we have few labeled data. Okay, and that should be much better than starting from scratch, because if we start from scratch and we have few labeled data here, the model will suffer from the limited amount of data, right? And remember, variance will be very, very bad, right? Because we have very limited training data for that task. Okay, did you get the idea here? So we will train a model first on the task for which we have lots of data, and then we continue training on the primary task. That's transfer learning. The second one is called multitask learning. Here, we don't do it in 2 steps like that. We do it actually in 1 step. We train the model on more than one task simultaneously. And that can happen only if, for the same examples, we have labels for different tasks. So for example here, this image, we have labels for segmentation and we have labels for the depth. So we can train the same model now, okay, for both tasks. So we might have here, of course, there are multiple architectures. We might have separate output layer for each task, or we have one output layer with different nodes for the tasks. And this is what you will see in the project. It's very simple multitask learning that you will do in the project, where the output layer actually will learn multiple tasks together. Right. What is the difference between transfer learning and multitask learning? Yeah, this is for 1 step. Okay, this is 1 step, and these are 2 steps. Here we assume that we have lots of data for that task and few for here. But here we do it together. But what's the intuition? Yani, what's the benefit? If we have few labeled data for the first one and few labeled data for the second one, because we are talking about the same examples here, right? Yani in transfer learning, the examples might be completely different. The images might be completely different. Here we have to have the same image, same set of images, but labeled for the different tasks. But what's the intuition? Yani, why we should learn 2 things at the same time? How could that benefit both actually? We only end up with one model, but that one model is able to predict for both tasks. Yeah. So what's the intuition here? Can you give me something from real life that when we learn 2 things, we might learn them better than learning each individually? Yeah, so you mean predicting a disease for a patient might help predicting another disease for the same patient, right? So even if these 2 diseases are different, but predicting one might help, or learning how to predict one might help predicting the other one. Yes. Okay, and we do that all the time, by the way. Okay, maybe studying 2 courses that are related at the same time might help you, like calculus. If you if you learn calculus in parallel to this course, maybe this will help you understand more the material that we study. Okay, so this is multitask learning. The third one is called self-supervised learning. Okay, self-supervised learning. We talked about supervised learning earlier, right, in the course, right? So with supervised learning, we have labeled data, and we learn from these labeled data. In self-supervised learning, it's still supervised learning. Still, we need to have labeled data to learn from. But the idea here is that we can generate these labeled data automatically. We don't need humans to go and label this data. Okay, for example, I have these images. I can mask part of the image and train a model to predict the masked part. Do I need humans to label this data for me? No, I can automatically black out part of mask parts of the image and I know that part, right? Because I have the original image, and then test the model, train the model to predict that part. And of course, now I can test, of course, and evaluate the model because I know which part I removed, right? So I can generate this way lots of automatically labeled data and train the model on it, right? This is called self-supervised learning. Why is it self-supervised? Labeling. Yeah, it's yes. It's not by the AI. We it's by definition we can automatically generate the label. Okay, we don't need even to we don't need to build the model to generate this. It's just that we have the data, we mask part of it, and ask the model to predict that part. So we can actually generate lots of data this way. If we have images, we have millions of images. Each image actually we can generate maybe tens or hundreds of versions of it to predict parts of the of that image, right? Yeah, exactly. And that's called generative self-supervised learning. Why? Because the model now is trained to generate what is missing, generate something that is completing the example that is given. Okay. Type. Why would we do that? What's the benefit of having such model? Okay, so yes, we can generate images, but regardless of this specific task, can we use that for something else? Why would such task? It's similar to this, right? Why would such task useful for something else? Okay, forget about this specific task now. Okay, the idea of self-supervised learning. Okay, to automatically generate training data and train a model on that generated data. Okay, we have a model now. Okay, yes, this model can do a prediction for this. Yes, but can we use it for something else? Okay, in the previous slide, we talked about transfer learning, right? Can we use that model now for transfer learning? Yes, of course. Okay, but now the difference is that in the previous slide we said we have to have lots of labeled data, right? For the secondary task. Now we can generate. We have lots of automatically generated, automatically labeled data. Okay, and we can use that for transfer learning for other tasks. Okay, now that model at least learns how to understand images, how to represent and understand the structure of images, right? So we can make use of that model and maybe further training it on for another task. Okay, so that's a kind of self-supervised learning called generative self-supervised learning. Now for text, how can we apply the same idea? You said something about that. Yeah, so we can mask the last word in a sentence, okay, and ask the model to predict it. We know it, right? As a label, we know which word is that. Or generally, we can mask any word within a sentence or any set of words, not just one word, and ask the model to predict what are the words that were masked. Okay. Sorry. Another type of self-supervised learning is called contrastive self-supervised learning. Here, we don't auto-generate the label data by masking. We generate auto-label data by contrastive learning. In contrastive learning, we show the model examples of similar objects and examples of different objects. And we can do that automatically. For example, you see this image of the dog? I can generate a version of this by different ways. One of them is to change the colors. Still, this is an image about a dog, right? And we can say that these two images are similar, right? So we call this positive pair. I can generate a negative pair that shows two different things by taking the same dog image and pairing it with a random image. Okay, any random image, most probably it will be different than this image. So now I can train, if I have a list of, or I have a large amount of images data, then I can generate these similar and different pairs, and I can train the model to predict if that pair is similar or not. Okay, so that model now learns a little bit about similarity between objects and can also help in other related tasks. Okay, so same idea here. We can use this for transfer learning for another primary task. Right. For text, how can we do something like that? The structure of? What do you mean by the structure of sentences? Remember, here we need to have pairs of similar, any positive pair and negative pair. Positive pair means two things that are similar. And okay, so yes, so rephrasing a sentence will be similar to the same sentence, right? That's a positive pair. How about negative pair? Huh? Yeah, taking a random sentence, right? Taking the sentence with a random sentence, okay? Or taking, for positive pair, taking a sentence and the next following sentence. This is called next sentence prediction. Okay, these will be similar, of course, not different. Okay, that's a positive pair, and negative again we can use random sentences. For all of these, especially the self-supervised learning techniques, we might have auto-generated label that is wrong. Yani, for example, maybe I will get randomly an image of another dog. Okay, it can happen, but what's the chance? That's considered some noise in the data, but with the large amount, this noise should not be very problematic. Okay, is that clear? Again, now we can use these models for transfer learning. Yes. It's not a word. It will be a sentence. Yeah. Yeah. But you need to know to do it automatically in the right position. Okay. Remember, all of that is self-supervised, so you have to be careful in generating good data automatically. Okay. You don't throw not anywhere and say these are different. Okay. Yes. Any questions? Okay. Very good. The last idea that we'll talk about in this session is data augmentation. Before we get into data augmentation, how is transfer learning, multitask learning, and self-supervised learning related to regularization? It's part of a regularization session, right? How is that related to regularization? What is the goal of regularization? So to improve the performance, to improve the generalization performance, right? Right? And these techniques actually aim to do that. Okay, by training on more data on related tasks, we can have better generalization for the models. Also, data augmentation is doing something like that by again automatically generating data that is good for training. For example, if I have labeled images, maybe in this case, if the image or what is the object in the image? Okay, object maybe recognition. So that image, for example, the original image has a bird, right? I can, from that image, I can generate multiple images that also will be labeled similarly, having a bird. Like, for example, flipping the image, rotating and cropping the image, scaling the image up or down, right? Changing the color of the image, blurring the image, and so on. So there are many ways by which I can transform the image somehow while keeping the same label, the same label, okay, the same label. And now adding these automatically generated label data to the training data, hopefully that will improve the training of the model. Okay, so that's the idea of data augmentation, is to add automatically new label data to the training data so that we have more data than before. Okay, and that hopefully will improve the generalization of the model. Good question. Can you give me example of task? Because it depends on the task. يعني, for example, sentiment analysis. Okay, that's usually the easiest example. If I have reviews already, okay, that are labeled, I can, from each review, I can generate some reviews by maybe paraphrasing. Okay, with keeping the same, hopefully that hoping that the paraphrasing will not change the sentiment of the text, right? In that case, I can paraphrase multiple times. I can add that to the data. Another idea is called back translation. You take the text, translate it into another language. Okay, يعني مثلا the text is in English. Okay, I will translate it to French. Okay, auto translate it to French, of course, and then auto translate it back to English. When we do these two ways, we will get most probably, we'll get different text. Okay, they will be different, but they should have the same sentiment in that case. Okay, so this is an example from text. Is that clear? Okay, very good. With that, we are done with the regularization session.